Throughout history, our biggest leaps in technology have occurred as a result of new materials becoming available. I've shown you how it took humankind centuries to master iron and steel, culminating in the explosion and growth during the Industrial Revolution. How the accidental discovery of age hardening allowed aluminium to take humans into the stratosphere in droves, and how silicon forms the backbone of this age of information. But today, we're going to discover the next great leap in material science: carbon fiber reinforced plastics. Carbon fiber, and its even more futuristic brother, carbon nanotubes, have been touted as the next great innovation that will allow humans to build amazing structures that were once unimaginable. Elon Musk recently revealed an enormous carbon fiber reinforced plastic cryogenic fuel tank, the largest fuel tank that has ever been created for space flight. The first carbon fibers were produced by Thomas Edison and Joseph Swan for use as filaments in their new electric incandescent lamps. The carbon fibers they created were produced by carbonizing plant threads like cotton, wood, and bamboo. This material did not have the tensile strength of today's carbon fibers, but they allowed Edison and Swan to replace the expensive platinum filaments being used earlier. The carbon bamboo filaments Edison developed lasted up to 1,200 hours, and they were the norm for 10 years until tungsten filaments replaced them. Researchers all over the world took notice, and just a month later, the Japanese Industrial Research Institute began investigating how to make their own fibers from polyacrylonitrile, or PAN for short. The majority of today's carbon fiber is produced with PAN, even though it is an expensive byproduct of oil production. It yields a fiber with a much higher percentage of carbon than rayon, and it's easier to manufacture. Dr. Shindo created long strands of this PAN material, which he stabilized by first heating it to around 250 degrees for up to 2 hours. This rearranges the chemical bonding to create a thermally stable ladder bonding. These fibers were then heated again to around 1000 degrees in the absence of oxygen, which expels the non-carbon atoms in the material, leaving tightly bonded carbon atoms arranged mostly in the direction of the fiber. This material was both heat and chemical resistant. It had fantastic tensile strength and didn't rust. Specialized industries like aerospace immediately saw its potential to help spacecraft break the grip of Earth's gravity, and golf clubs, tennis rackets, and racing bikes started to be made with the cheaper off-spec fibers that the aerospace industry could not use. Despite its high price, demand for the material kept growing, and by 1980, 1,000 metric tons were being produced a year. But it was still a notoriously difficult material to work with, and many still doubted its ability as a structural material. During the development of the McLaren MP41, one skeptical engineer is said to have picked up a piece of carbon fiber composite, just like this, and easily snapped it in half, declaring that the material was too weak and brittle to be used for the ambitious carbon fiber composite monocoque. But he was breaking the material across the fibers. If he had attempted to break it along the fibers, he would have had serious difficulty. You see, carbon fiber is made from these tiny thin fibers. This is a picture showing the size difference between a carbon fiber and a human hair. The carbon fiber is a smaller one. These tiny fibers by themselves can't be used as a material. We first have to bind these long strands of fiber together with a plastic resin. Otherwise, they're just a flimsy fabric that can't hold any load other than tension. Here you can see a solid piece of carbon fiber, where the fibers are surrounded by white resin. But this technique causes some problems for engineers when designing a product with this material, because the plastic is weaker than the fibers. This is a unidirectional layer of carbon fiber held together with resin. If we pull it this way, along the fibers, it has fantastic strength, because the fibers are in the same direction as the load and thus can resist it. But if we pull it this way, there is no continuous run of fibers to resist the force. Instead, the resin matrix gets pulled apart, and the fibers add very little strength to the material. To combat this, engineers will layer the fibers on top of each other. Here we have a 0-degree layer on top of a 90-degree layer, so the material properties are the same in those directions. But now the 45-degree direction is weaker. We can keep adding more layers until we have similar stiffness in all directions, but eventually the thickness of the material will become too great. We reach another problem when we remember there is nothing but the resin matrix holding these layers together, and sometimes that fails and we get delamination of the layers. This is why you often see the carbon fibers woven into a fabric like this, but again, woven fabrics can only be so thick. We also need to worry about the drapability of the material, as these fabrics need to be shaped over molds, and a very thick material like this can make that job very difficult. These issues create a whole lot of work for engineers working with composites. But with experience, we have learned to use these unique material characteristics to our advantage. The designers of the MP41 managed to create such a strong monocoque with the material that when the car did crash, it silenced many of its doubters. We can tailor the fibre directions to optimise the material properties. Here we performed a tensile test on a tiny piece of carbon fibre composite with fibres only in the direction of the force, creating an incredibly rigid structure that barely deformed through the test and managed to hold 5.3 tons before breaking. But stiffness like that is not always desired. For example, in the event of a crash, you want your car to crumble and deform to absorb as much energy as possible. And so composite noses of F1 cars are designed to fragment into millions of tiny bits, and this helps absorb energy and decelerate the car more slowly. Thanks for watching.